Okay, looks like Tegrity is recording. Hopefully this won't just stop in the middle of what I'm talking about again, but if it does, maybe we'll just go to our lab early and do everything there. We all have computers and more PowerPoint and everything. All right, any questions about the quiz or anything before we start? Everything's good? Good enough? I think whatever marker I use to draw on the board is like oil. It's like it's not coming off. Oh, wait, there. Just need the oil in my fingers to count. That's pretty. Anyway, lesson learned. Okay, yes, so for your quizzes, I will get those graded tonight and put on Angel so you'll know tonight what you got. I'm sure you're just like, I'm dying to know. All right, so let's go ahead and move on, and we'll just kind of recap a little bit more thoroughly what we did last time, because last time was a lot more confusing than the time before when we were talking about like samples and variable levels. But last class we talked about things like standard error and alpha and null hypothesis significance testing, and it was confusing. So just to kind of review, we talked about standard error, and we talked about how this really helps us to understand how much variability we expect to have in our statistics, right? So how much variability we expect to have in our estimates based on participants in our sample. So we kind of talked about it in terms of, like, we looked at standard error of the mean, right? And we looked at it like how much variability in our sample mean is due to random variation in the population that would represent that sample, and how much is due to the specifics of our sample. So that's kind of what we're trying to look at when we look at standard error. So we looked at that. We also talked about that central limit theorem, which says that the larger our sample is, the better it will estimate or kind of mimic the variability in the population. And then we talked about methods for comparing our sample statistics against population parameters, like in the case of a z-test, or an other known value in the case of like a t-test. So we talked about those things, and we learned how to calculate the t-value. It's that number that lets us know whether the difference between our known value, like Omaha shoe size, whether the difference between our known value and a sample value is large enough to be considered statistically significant, right? So we know there's random fluctuation. Is the fluctuation that we're seeing in our sample just random, or is it significantly different from the variation we see in the population? So that's what we're looking for when we look at statistical significance, right? Is this variability significantly different? And we saw that this t-value maps on to a well-known t-distribution. And what was nice about the t-distribution is it fluctuates based on sample size, right? So if we have a smaller sample, we can use this distribution. And so that table that we looked at, it accounts for that, and it changes our p-value based on how many people you have in our sample. And if we have a larger one, we can use what's basically a normal distribution, right? So we like the t-distribution because it fluctuates based on sample size, and it allows us to determine the probability of getting a particular t-value given our sample size. So we can use this t-value in conjunction with the alpha level to see how likely it is that we would get the t-value we get in our sample based on our sample size. So we talked about that, and then lastly we kind of tried to wrap our heads around p-values and alpha levels and statistical significance. And again, if the p-value associated with our t-value and degrees of freedom, so the p-value we get for our t-value and our degrees of freedom, if this is less than 0.05, we can safely assume that the t-value describing this difference is significant. So that the difference we see in our sample reflects the real difference that we would see in the population. So that's what all of that is kind of saying. And so we're going to pick up from here today, and we'll start talking about effect size and confidence intervals, and we'll talk about a handful of statistical tests that we can do with the t-distribution, so t-tests. And then we'll kind of end by talking about another distribution, the f-distribution. So it's kind of like a more elaborate version of a t-test, and it uses a different but similar distribution And so that's the one-way ANOVA, so we'll go through that last. But let's go ahead and start with effect size, which is related to significance level. So last class we mentioned that as long as our t-value is associated with a p-value of less than 0.05, then it's significant. And we see that in this t-distribution, our degrees of freedom influences our p-value. So whether or not our t-value is associated with a significant p-value. And you can see on this distribution here that basically here's our degrees of freedom. It's based on our sample size. It's basically n minus 1. So here's our sample size. And what you can kind of see is a trend that the larger your sample size is, the lower your t-value needs to be considered significant. So let's just go ahead and look at our 0.05 two-tailed test. That's the standard we always use. And you can see that if you have a sample of 1, your t-value has to be huge. It has to be 12.71. That's good. Like, you shouldn't really be basing a lot of your judgments on a sample of 1. But you can see as sample size gets bigger, the t-value gets lower and lower. And so if you have a large sample size, you only need a t-value like 1.96 to get significance. And this is good to know because it's basically showing you that it's easier to find statistical significance if you have a large sample size. And so this means that with even like with really large sample sizes, even minimal differences will be significant. They'll be statistically significant. So for example, here you can see that I have IQ scores for men and women. So men have an IQ of 100.02. We're way smarter. We have an IQ of 100.04. And what you can see here is that if you have a sample size of 70, so if you sample 70 men and women, this is not a statistically significant difference, right? It doesn't matter. And we know that. We're looking at it, we're like, it's 0.02 points difference. It's not a big deal. However, it's important to know that if you have a sample size that's close to like 900 million, this difference will be considered statistically significant. And it sounds ridiculous to say sample size of 900 million, but when you think about nationwide studies that take place, this sample size may not be that uncommon. And so it's important to know that what you want to look for significance, but you also want to look at meaningful. Like, is this a meaningful difference? Is this practically significant? And so what we want to go through now is effect size, because this helps us to determine if a statistically significant difference is meaningful. So when we look at effect size, that helps us. So we'll talk about effect size and see how that's helpful, but to better understand why effect size is helpful and how it works, I want to look a little bit more at why sample size influences our statistical significance. So we know the larger the sample is, the more likely our t-value is associated with a significant p-value, right? The larger the sample size, the lower t-value you need to reach statistical significance. And the reason for this is that sample size is the denominator when we're calculating standard error. So all things being equal, here's our standard error formula. All things being equal, the larger the sample size you have, the smaller the numerator of the standard error, right? Because we're dividing by this. So the bigger this denominator, the smaller your numerator. So the bigger sample size you have, the smaller standard error you will have. This is important because standard errors are the denominators in our statistical tests. So having a small number in the denominator leads to a larger statistical value, which means higher levels of statistical significance. So you don't have to like super memorize any of this stuff, but I just think it's important to point out the reason sample size influences our statistical significance is because we're using sample size to calculate statistical significance, right, our t-values. So bigger sample sizes make smaller standard errors, and smaller standard errors make bigger t-values. And we can see this worked out right here. So you can see that On this top panel, you can see I've got our N of 22. So here's a larger sample size. Down here is an N of 5. And this is the same information except for this sample has a sample size of 5. So if we look at a sample size of 2, we can see that here's our standard error is 2.41. So it's smaller. It's a smaller standard error when you compare it with the 5.05 standard error of the N of 5, the smaller sample size. So our standard error gets smaller if we have a larger sample size. And you can see how that influences our statistical significance, right? So in the larger sample size, we have a value of p equals 0.015. So it's significant, right? But in the sample size of 5, our p-value is greater than 0.05. So although we have the same exact numbers in here, the only thing that's different is the sample size. You can see it makes a huge difference. It makes a difference between whether this is significant or not. So I have written in here, size does matter. And then a smiley face. But so a size does totally influence our statistical significance level. And this is where effect size is helpful. So effect size gives us this indication of how large the effect is, regardless of statistical significance and regardless of sample size. So effect size brings in this idea of practical significance or having meaningful results. So the formula for effect size is D. You can see it right here. It basically renders sample size ineffectual. What it does is it back calculates the test statistic, like the t-value. It back calculates it so that you're dividing by the standard deviation and not the standard error. So as you can see here, like these are the t and the d are basically the same formula, except for instead of dividing by the standard error, which is influenced by sample size, we're dividing by the standard deviation, which is not very influenced by sample size. So we're basically taking sample size out of this equation. And so you can see that for both of our example sample sizes down here, the standard deviation is the same. Wait, where's that? Yeah, there, sorry. The mean is the same and the sample size is the same. And you can see that when we actually go through and calculate this, our D values are the same. Our effect sizes are the same in the 5 and the 22 sample, where our T values were kind of wildly different, one being significant and the other one not being significant. The D values are the same. So you can see the same effect is in both samples, right? We're getting the same effect. And so you can see that you get the same effect size. And so as far as knowing if your D is significant or matters, we don't really compare it against the distribution. We just have some rules of thumb for how big that effect size is. So basically, D values that are lower than 20 are considered small effect sizes. So you can have a small effect even if it's significant, so it might be statistically significant, but you can see the D is small, so there wasn't that big of a difference. There's not that big of an effect. In contrast, a D of between 0.25 and 0.75 is considered a medium effect, and Ds larger than 0.80 are considered a really strong effect, right? Like a large effect size. So, for example, like let me go back here real quick. You can see our D is 0.57. Regardless of our sample size, we have this effect size. And when we look at our kind of rule of thumbs, we can see what kind of effect size is that. It's a medium effect, right? It's a pretty good effect, actually. 0.57, that's pretty meaningful. So if we had a sample size of 5, we would say it's not statistically significant, but it's a meaningful effect. So maybe we should look at this in a larger sample. Whereas if you had the sample of 25 or 22, you already know it's statistically significant, but now you can say it's practically meaningful too, because it's a medium effect size. It's a pretty good effect. It matters.
So the effect size.
Oh,
sorry. So the higher the effect, the more meaningful it is.
Right, basically. And again, so we'll talk about that in just a second because context is important. But what's nice to know is like when we look at our IQ difference with a sample of 900 million, it's statistically significant, but if we calculated the effect size, it would be minuscule. So you can say, I know that's significant, but it's not that meaningful. Whereas if you have a small sample size, you might not get statistical significance, but you can say it's a meaningful effect. So pay attention to me.
So it just takes away the advantage that large sample sizes have.
Right.
That's what it does.
That's pretty much exactly what it's doing. And so again, kind of putting it all together, it helps you get a better idea other than that hard and fast cutoff rule where it's like, oh, if it's less than 0.05, it matters. Well, maybe, but also, does it have a good effect? Does it have a meaningful effect size? And yeah, as always, everything has to be looked at in context. So regardless of effect size or statistical significance, whether the findings are meaningful really depends on what you're studying. So I always like to bring up the example of aspirin. So what was it, in the 80s? Everybody started taking aspirin to help reduce your likelihood of getting a heart attack. And when you look at the study that was done, the effect size of doing that is a 0.06. So it's a really small, pretty ineffectual effect size. However, the outcomes are huge. Like aspirin is cheap, it's readily available, it's pretty harmless to take one a day, and the outcomes like not having a heart attack, that's a big deal. So it's basically like for such a simple thing, you could have a huge benefit. And it may not like really reduce the likelihood of having a heart attack by that much, but the little amount that it does, it's totally worth doing it. So that's an example of having a really small effect size, but it being a really meaningful finding. And especially like when we do studies where you're trying to predict whether someone will die or not, a small effect size matters because it's like, oh, you mean if I do this, I might not die? Well, then I might go ahead and do it anyway, even if it might not let me die. Oh my gosh. We'll stop there. But yeah, so, and obviously in context, you know, that we've talked about the IQ difference, that it might be statistically significant, but it's probably not meaningful. So basically, this kind of stuff helps you to be aware of times when the sample size might make something significant that's not really that meaningful, or when small sample sizes may make something that's very meaningful, not statistically significant, or sometimes when even very small effect sizes are meaningful and might save lives or stuff like that. So knowing this stuff kind of helps you to better interpret all this information and understand what it means. Although sample size isn't necessarily everything, the central limit theorem does tell us that the larger your sample, the more likely you are to get people with characteristics that better represent the population, right? So honestly, part of the reason we do build sample size into these estimates is because it does get us more accurate representation of the sample. So sample size is important. It's better to have a larger sample. But that doesn't mean that findings with a small sample aren't meaningful, right? So sample size, it is good to have a larger sample size, but it doesn't mean you can't find important and meaningful things with a smaller sample. And so like your book says, when used together, tests of statistical significance and measures of effect size can provide important information. That's my shorthand. He actually says information. Regarding the reliability and importance of statistical results. Of course, our own judgments about the meaning, causes, and consequences of our results are also important factors. So stats can't tell us everything. We need to be knowledgeable so that we can best interpret the findings. So effect size is an excellent thing that helps us to kind of see how big the effect is and if it's meaningful. Along the same lines as effect size, a lot of researchers advocate for the use of confidence intervals. And these are kind of like a good indication of how reliable or accurate our sample statistics are. So let's talk a little bit about confidence intervals. So confidence intervals are used to give a range of values that let you be a certain percentage sure, like 95 to 99% sure, or confident that the mean of the population you sampled from falls somewhere within that range. So that sounds really strange and confusing as I hear it coming out of my mouth. So let's talk more about this. we'll clarify with the example of IQ. So let's say I'm measuring IQ in my sample, and so in addition to getting like the mean and the standard deviation for the IQ scores in my sample, I could also establish a confidence interval around that mean. So let's say that I do that. I have a 95% confidence interval that ranges from 92 to 103 IQ points. So this confidence interval would indicate that I'm 95% confident that the average IQ for the population that my sample represents, the average IQ falls between 92 and 103 IQ points. So instead of just reporting like the mean and the standard deviation, the standard error, we can kind of put all this information into this range of scores. So let's look a little bit more closely at how we calculate confidence intervals, so then maybe you can understand what's happening with them a little bit better. So basically they tell you how confident you can be that your value falls within a range of values. So to calculate a confidence interval, you need a couple of familiar pieces of information. So we need the sample mean, right? That's the X bar. We also need the standard error. That's this guy, right? So the estimate of how much error is expected in our sample statistics. So we can kind of put that in there as well. Then the last thing we need, which is a newer piece of information, this is this like little T95. This is the t-value associated with a two-tailed test with our degrees of freedom and a specified alpha level. So let's walk through that one a little bit more. But for a 95% confidence interval, you'd use this one. If you wanted to establish a 99% confidence interval, you'd use this one. So let's go ahead and walk through how this is calculated with a nice example. Let's say that we asked kids in a classroom in Dundee to guess the average temperature in Omaha in January, right? So we go to this classroom in Dundee and we're like, what do you think the average temperature in January is? And here's the stats we got. So let's say that we asked 22 kids. The average report of the average temperature in January was 25.59 degrees, so they know it's cold. We have a standard deviation of 11.29, so we know the scores range between most of the scores range between 14 and 36. And we have this standard error. If I plug these numbers into the formula to calculate a 95% confidence interval, it will give me a range of scores that tells me that I can be 95% sure that the population's guess of average January Omaha temperatures falls within this interval that's represented by the statistics I got from my sample. So here's our confidence interval formula, and we have everything we need to solve it except for this T of 95. So where do I get this T of 95? This is a t-value associated with a two-tailed test and an alpha level of 0.05. So we're 95% confident that this is the range of values. So we're only 0.05% confident that it's not in there, right? So we want an alpha level of 0.05. And so to get that T95 value, I need to find the value associated with a two-tailed alpha level of 0.05 test with my degrees of freedom. So I had 22 kids in my sample, right? So our t-test degrees of freedom is n minus 1. So it would be 21. So we have to find the alpha level. So here's our 0.05 alpha level, right, for a two-tailed test, and associated with degrees of freedom, 21 degrees of freedom. So if you put those together, you can see that that T95 value is 2.080. So what we're really finding is the T value I would need to have a cutoff of less than 0.05 for my alpha level, right, with the amount of degrees of freedom I have. So it's kind of like back calculating our t-test, right? It's just using the same pieces of information in a different way. So it's a little bit confusing. But if we go ahead and plug this in, we know that our t-value is 2.080. That's where we got it from that test from that table of T distributions, and we needed to know the degrees of freedom and the alpha level to find it. Yeah.
Could we briefly talk again why you
Yeah.
chose the 0.05 column?
Okay, yes, so you are trying to establish a confidence interval that says that you are 95% sure that this value is right. And so if you subtract 95 from 100, you get 0.05, right? Or you get 5. But so this 95 is associated with 95% sure it's right, or 5% it might be wrong.
Gotcha.
Does that, yeah.
Okay.
It is
So
a
always
little confusing.
subtract the number from 100.
Yeah, you could do that, yep, or most of the time I'll just be like, okay, 95 confidence interval, that's associated with a 0.05 test. And so if you think about it, what's the 99% confidence interval? Right, 0.01. So we'd have to go two-tailed 0.01 tests. So if we wanted to establish a 99% confidence interval, we'd have 2.831.
So we always want to look at the two-tail.
Yes, you always want to look at the two-tailed because we're establishing a confidence interval, and the way we do that is it goes around our statistic. So the interval is above and below the statistic. So you want to use a two-tailed test.
Okay, thank
Yep.
you.
Yeah, no problem. I know it's very confusing, and I love the questions because that helps clarify it for everybody. So that's where we got that value. So we plug it into our formula. And if we do that, we basically find this range of scores. So our 95% confidence interval around this mean of 25.59 is 20.58 to 30.60. So it's a range of values, right? It's almost 10 points, a range of 10 points. And when you interpret this confidence interval, what you can basically say is that you are 95% confident that the mean for the population that our sample represents falls between 20.58 and 30.60. Do you want me to say that again? Okay, so with this 95% confidence interval, what you're saying is that you are 95% sure that the mean for the population that this sample represents is between 20.58 and 30.60. So based on my sample's average guess of 25.59 and the variability I know is around that mean, and the standard amount of error associated with my statistic and the t-value I would need based on my sample size and a predetermined alpha level, based on all of that stuff, we kind of back calculate this and say that I am 95% sure that the population guess for Omaha temperatures in January is somewhere between 20.58 and 30.60. Does that make sense? So it's basically saying we know there's error in our sample, we know that we get some random variability, and instead of saying, I think it's this value, this one value, 25.59, you're saying, I am 95% sure that the value falls between these two things.
And the reason why we said we are confident is because the mean does fall within it.
It totally does. In fact, the reason you're confident is because you've used that 0.05 alpha level to establish a 95% confidence interval. So you could say, I'm 5% confident that it doesn't fall in here, but you're 95% confident that it does fall in here. Because again, it's all kind of based on that alpha level, that 5% error that we're willing to accept and say, 5% of the time we're wrong, but 95% of the time we are right. So I'm 95% confident that this is what the population looks like.
So it would be appropriate to say, if it was out of those numbers, that you would say we are 95% confident that it does not?
So you could
What
say.
phrase would you use?
So I don't know that you would say I'm confident that it's not ever. You could say that we're not confident that it's within this range, maybe. And you'll see what's kind of cool, and we'll talk about this later when we talk about t-tests, is, and I don't want to blow your minds, but if you're like doing a test, if you're saying that I think there's a group that is statistically different from my sample. If their mean does not fall within here, then they are different than you. We'll talk about that more there, but the value you're trying to find should be in here. If it's not in here, it's not significant. If it is in here, it is significant. If you don't understand what that means right now, it's okay. Because I have written down here, like, let me tell you about it, and then I'm like, don't talk about it yet. So we'll talk about it more in terms of the t-test where you can actually see somebody's mean is not in here. And so it is different. I'll stop there for right now. Okay, so this is confidence intervals. Oh, and look at that. I even wrote it down. Sorry, I forgot. So this is basically what we can say with this value here. And they're kind of nice to calculate them because then instead of just saying this score and this standard deviation, you're saying here's the range of scores that I think should be here. All right, any questions about confidence intervals right now? No? Yeah. I think sometimes some journals are like, we want you to report effect sizes and confidence intervals. And I think part of it is to show you how much error there is in your calculations. So if you think about it, and this might be too much, but if your confidence interval is huge, that means that you're not, like, there's a lot of scores it could be. It's not very specific. However you're measuring this or whatever, it's not giving you a very good specific value. If your confidence intervals are tighter like this, that means you're pretty sure that it's within this small sample. So you can be very specific about what you're trying to talk about. So it kind of gives you a measure of variability in your sample and in your scores. But I know I don't calculate them very often, but some journals are like, no, you need to establish confidence intervals on your graphs. And we'll see those, and those are kind of a bit more helpful when you see them. They're like these little error bars that you put on your graphs that say, I think this value is here, but it could be a little bit lower or a little bit higher than here. So they look better on graphs. But effect sizes, when they do kind of like to see reported, because it's like, not only was it significant, but it matters. And that makes more sense to me. But yeah, so you can use it in a couple different ways. All right, any other questions on that? All right, the nice thing is you don't have to calculate these on your own. We went through how to do it, but SPSS, you can just be like, click, and here are your confidence intervals. So we will do that. But it's helpful to kind of walk through it to understand what it's doing and what these values mean and how you would use them. So yeah, people generally like to see confidence intervals because they give you a range of scores that surround the sample statistics, but they're also pretty easy to understand once you go through them. And what's nice is, unlike effect size, they're in the same units that they're in the same metric, right? So effect size, you're like D equals 0.57, what does that mean? Here you can say, I know what units, I know what this range means. So it's a little bit more meaningful. But so all of these things together, right, statistical significance, practical significance, confidence intervals, all these things together are pretty helpful in helping us to understand the larger picture of what your stats are trying to tell you about the population, right? They're basically telling you how representative these stats are of the population to which you're trying to infer, right? All right, any questions on that? Oh, yeah, there. All right, do you want to take a break now or later? Or both? No. So basically, the next thing we're going to go through are these t-tests. And it might be easier to just kind of plunge through those and take a break, because you're going to want to break before ANOVA, because ANOVA is, if you don't, we'll go through it, but I'm just like, ooh. Yeah. All right, let's talk some t-tests. Let me throw this down here. Okay, so t-tests, it's nice because we actually started talking about these last time, right? So it's not a totally unfamiliar concept. So we started talking about these when we compared our Omaha shoe size to our sample of Omaha women and their shoe size. But we're basically going to extend this idea to some more, I think, more interesting and more meaningful and more applicable comparisons. So we'll be talking about the independent samples t-test. It's similar to our one sample t-test, except that instead of comparing our group mean against some this known value, you're going to compare it to another group mean to see if these groups differ. So that's very meaningful, very helpful to know how to do that. Then we'll also talk about dependent samples t-tests. This is basically identical to the independent samples t-test, except for in this instance, the samples are related somehow. So they're not independent samples, they're dependent samples. And so this is typically the kind of test we do when we're measuring the same people twice. So when we're doing a pre and post test. So we have an intervention, we measure people before they get it and after they get it. They're the same people, so it's dependent, and we use this kind of dependence t-test to see if they've changed significantly. So we'll go ahead and start looking at that now, and then in the end we'll look at these one-way ANOVAs, which are basically like instead of just comparing two groups, you can compare as many groups as you want with one really complicated analysis. So it's so nice. No, it'll be okay. In fact, there's a lot of stuff we'll go over that you don't ever have to calculate again. You just have to understand what it's trying to say so that you can interpret your output. But let's go ahead and start simply with a review of the one sample t-test. And when we talked about this last week, we talked about the z-test and the t-test, right? And how they're similar, but they're different in that both of these tests allow you to compare your sample mean against an already known value, right? So in the z-test, we're comparing our sample mean with the population parameter, but we have these additional constraints, right? You have to know the population standard deviation or standard error. You also have to have a sample size greater than 30. And because the t-test does the same thing without these constraints, we pretty much always use the t-test instead, right? And we can use it even if we don't know the population parameters. We can use it even if we have a small sample size because the t-distribution takes sample size into consideration. And we kind of were like, oh, you can kind of forget the z-test. Like, it's good to know what it does, but I honestly don't know anybody who's ever used one in my life. So t-test, though, we use all the time. So we talked about the t-test. You did it in your homework. We did it in the lab. And so you're familiar with this test and what it does and interpreting this output. So that's really nice. We don't have to totally go through that again unless you really want to. But we can kind of just go ahead and move into independent samples t-tests, extending this to different independent groups. So with our independent t-test, instead of comparing our group mean to some known parameter, now we are comparing our group mean to another group mean. So we're just comparing two groups to see if they are different. And so this test allows us to do some really awesome and very meaningful comparisons, but it does have some constraints. And so you can see here the types of variables you need to do this test. If you don't have these variables, you can't do this test. So our independent variable, the variable that we think is responsible for the differences in the dependent variable, our independent variable can only have two levels, right? So it has to be a nominal variable, and it can only have two categories. So we can look at things like men versus women, short versus tall, high versus low, early versus late. Basically any type of category that only has two levels. So that's one constraint. But it's okay because we are actually interested in a lot of categories or a lot of variables that only have two categories. So it's okay.
I have a question. Does it have to be opposites like that, like male versus female, or can it be like class A versus class B?
Yep, totally. Yep. Anytime there's just two levels. Yep. If you had 3 levels, that's where we start talking about ANOVA. But so 2 levels, you can do this test. The other thing you need is your dependent variable has some limitations too. The variable we think changes depending on the independent variable. Our dependent variable has to be a scale variable. So it has to be scale level. So it's supposed to have equal intervals. It doesn't have to have a meaningful zero, but it should have equal intervals. So things like height, income, hours of sleep, anything that has an equal interval, temperature. So it should be a scale variable. And so basically anytime you have these conditions, you can use this kind of a test to see if these groups differ.